In this video, I'll show you guys 3 ways on how to find the explicit formula for this recurrence relation. Have a look right here. This is the first way. And this is the way that either you will like so much or you will hate it so much. Because we are just going to be writing down the first few terms and try our best to see if you can find a pattern on that or not. So, have a look. N starts with 0, and the first thing that we have is 5. Then, based on this, this is telling us we have to do 2 times the previous. So 2 times 5 is 10, and then minus 2 to the first power, which is 2. 10 minus 2 is 8. And then we continue. 2 times 8 is 16, minus 2 to the second power, which is 4. 16 minus the minus 4 is 12, and then continue. 2 times 12 is 24, minus 2 to the third power, which is 8. 24 minus 8 is 16. And then 2 times 16 is 32, minus 2 to the fourth power, which is 16. 32 minus 16 is 16. And then 2 times 16 is 32, minus 2 to the fifth power, which is 32. 32 minus 32, of course, that will be 0, and then so on, so on, so on. Now, we're just going to focus on these numbers and see if we can find a pattern on this or not. And maybe you want to pause the video and try this first, because this is not so easy, right? Because this is not geometric, this is not arithmetic, this is not nice. So let me know if you have any specific strategy for this. Here's mine. Right here, we see that we have 2 to the nth power. And notice this right here does not base on the previous term. And usually when you have 2 to the nth power, it's a good hint that we should be looking at the powers of 2. Well, n start with 0, so I will write down this right here. 1, and then 2, and then 4, and then 8, and then 16, and then 32, and then so on, so on, so on, right? Very nice. Now, I want to make a connection between these numbers and these. How can we do it? Well, have a look. How can we go from 1 to 5? You can say add 4, or you can say multiply by 5. How can we go from 2 to 8? You can say add 6, but better yet, you can say multiply by 4. Because if you said multiply by 5 here, and then multiply by 4 here, what's next? Multiply by 3, isn't it? 3 times 4 gives us 12, and then 2 times 8 will give us 16, and then 1 times 16 will give us 16, and lastly, 0 times 16 will give us 0. 0 times 32 will give us 0. What's next? It will just be negative 1 times 64, isn't it? So here again, it will be negative 1 times 64. So that will be negative 64 for the next number. Very nice, huh? So based on this, we can just write down formula already. An is equal to the following. The numbers in blue, they're just going down. It's arithmetic. That's very nice. And the formula for that is just 5 minus n, because n starts with 0. Then we see that the numbers in red, they are just the powers of 2. So I just have to do 2 to the nth power, and we are done. Again, as I said, this right here, it could be the one that you love the most, or it can be the one that you hate the most. Sometimes it's not so easy, because for example, if you look at the Fibonacci sequence, write it down, right? Write down the numbers. 1, 1, 2, 3, 5, 8, so on, so on, so on. And try your really best and see if you can find a nice pattern for that. Can you come up with the explicit formula for that? I don't think so, right? You do have to have a systematical way in order to solve this kind of recursions. And that's the second way, and also the third way are 4. So have a look. Here is the second way. Well, as I mentioned, this right here is called the recurrence relation, and some people will also call this to be the recursion, and some people also call this to be the recursive formula and difference equation, etc., etc. Depends on the kind and all that stuff. Anyway, though, hopefully you guys have taken differential equation, because I'm going to make a connection between this with the linear differential equation, in particular, maybe the higher order. So let me show you guys this right here. Suppose you have a higher order, let's say second order differential equation, let's say y double prime minus 3y prime, and then plus 2y, and that's equal to e to the 2t, like this. This right here It's a second order linear differential equation with constant coefficients. But this right here is not homogeneous because the right hand side we have the function, right? If this was equal to 0, then it's a homogeneous situation. Now, this is how we are going to do it. To solve this differential equation, what we do first is you consider the homogeneous situation. Namely, you want to solve y double prime minus 3y prime plus 2y is equal to 0. And the way to solve that is you start with a guess, if you would like to say that. Some people hate that because nobody likes to guess. Right? Just like guess and check. That's not ideal. That's not ideal. However, if you really think about it, you can see that there's only actually one good choice. Right here, you see the y prime, y double prime, they're just like a constant multiple of each other in order to have everything add up to be 0. And the only function that will make that happen is when y is equal to the exponential function. And we can write it as e to the some constant r times t, like this. Because again, if you differentiate this, you will get re to the rt's power. And if you differentiate that again, you get r squared times e to the rt power. And you see they're just a constant multiple. And if you plug that in, then you will be able to solve for what r should be. And then that's how you can get the solution to the differential equation right here. And this is again called the homogeneous differential equation. And usually we can put down the YH for this, right? So that's the idea. And in case if you're interested, I will tell you YH, this right here, you will get r is equal to, well, you pretty much will have to solve r squared minus 3r and then plus 2, right? So you can just have to make that equal to 0 and then it's r minus 2 and then r minus 1 equal to 0. So in another word, your e to the rt, your building blocks to your solution, I will tell you, is going to be e to the 2t and the other one is e to the 1t. So these two are your building blocks for your final solution, I would say. And we are going to do the similar thing right here. What we are going to do is, you see that we have the a sub n here, and then 2 times a sub n minus 1. This is the one that does not have the a or whatever, right? Just like this. This one does not have the y or the y prime whatever. You just ignore that for now. So let me just again write this down right here for you guys. This right here is the homogeneous situation. And all we are going to do is, I'm going to be looking at an equals 2 times a sub n minus 1. I'm going to try my best to solve for this. But this is not so bad at all. How come? Well, if we look at this carefully, this is just telling us multiply by 2 with the previous one, multiply by 2 with the previous one, multiply by 2 with the previous one, namely 2 to some power, exponential situation. This right here is telling us our homogeneous solution right here should just be, let me write down an, 2 to the nth power, right? Well, now you might be wondering, what if sometimes we have like something else? For example, for the Fibonacci sequence. For the Fibonacci sequence, you have an that's equal to an minus 1 plus an minus 2. It's not so easy to just look at this and then figure out what the base should be, right? So this is how you are going to do it. It's very similar to what we just did right here. When we have this, well, our initial guess is that an is equal to r, again for some base, and then raised to the nth power. In fact, this is how I solve the explicit formula for the Fibonacci sequence, which I have a video for you guys already from 3 years ago. So go check it out if you would like. Well, now I will do the work for you guys. An is equal to this, so I will just put down r to the n, which is equal to, here we have the 2, and then a sub n minus 1 is just, you put n minus 1 right here, so it's r to the n minus 1. And you see both of them have r to the nth power. We can just divide that out. You get 1 is equal to 2 times r to the negative 1. And of course, we could divide. It's because r should not be equal to 0. If r is equal to 0, we are not doing any math right here at all, right? Anyway, right here you can see that r to the negative 1 times 2 is 1. So that tells us r is equal to 2. Then you can just put a 2 back right here. And that's how we figure this out. And we only have one r because this is just, r to the negative 1 power. That's all, right? And this right here have two solutions because this is the second order. And you see this right here is n minus 1. So it's like the first level difference. That's the idea. All right, so that's good. That takes care of the homogeneous situation. However, though, for the particular situation, it's trickier, so pay close attention to this. Again, I will use this as the example. For the particular solution, if you look at the differential equation situation, well, you have to pay attention to the form of this function, which is exponential, namely e to the 2t. Well, the particular solution, you should have some constant multiple, let's say capital A, times this, which is e to the 2t. But here's the problem. If you put on e to the 2t, in fact, we have a duplication right here already from the homogeneous situation, right? So the way that you're going to fix this is that you are just going to multiply this by t. Why? You can check out my differential equation video on that. You can check out Dr. Plan's video on that. But for now, the purpose is just that I want to show you guys, you have to make sure this and that, they have to be linearly independent in order to come up with new solution. Because again, they are just the building blocks. Later on, you will have to multiply this by a constant, likewise that, to get the general solution. If you just have a times e to the 2t, this and that match, no good. So you just multiply by t, it will work out very well. Now, have a look. This right here, we have the homogeneous solution right here already. And some people will say this is an and then with the little h on the top with the parentheses, but this does not mean you take the derivative, right? So it has nothing to do with derivative in this notation. Now, here we go. We are going to focus on the particular solution. I will do this one in black. So here is the particular situation. Particular. There we go. Particular situation. Well, you will have to just look at what kind of function, what quantum sequence this is. We have 2 to the n. Ah, man, I'm going to write down an and with a little p right here, parentheses, because for the particular situation, we have 2 to the n right here. So this is also going to be 2 to the n with a constant in the front. Again, let's put on capital A for that. But just like this right here, this and that match. What do you think what we can do? Yes, all we have to do is just multiply this by n. That's it. No kidding, right? Again, I can do more videos on that if you guys would like. But for that, hopefully this right here is satisfying. You guys are satisfied with this already. Okay, once we have the particular form, then just go ahead, put them back to the original because we have to figure out what a should be. So this right here, I will just put it down right here on the left hand side. We have capital A times n and then times 2 to the n. And that should be equal to, we have a 2 right here. And then a sub n minus 1. Well, this will become n minus 1, likewise for that. So we have a and then n minus 1 and then 2 to the n minus 1. And lastly, we have the minus 2 to the nth power. And now we just have to focus on how to solve for capital A right here. And bye-bye differential equation. I'll see you guys soon. All right, now here's the deal. The left-hand side is still a times n times 2 to the n. Multiply. So you see 2 times this is just 2 to the n, which is nice. A times n times 2 to the n. So we have a times n times 2 to the n. And then again, we have 2 to the n times a times negative 1. So it's minus a times 2 to the n. Then right here, we have minus 2 to the n. Now have a look. This and that, they are the same thing. So of course, they can just cancel each other out. Very nice. And I will just move this to the other side and I get positive a times 2 to the n. That's equal to negative 2 to the n. So what does that mean? A has to be negative 1. So that's very nice. Right? A has to be negative 1. Now we can see that our particular solution here, an with a little p like this, a is negative 1. So I just have to put on negative 1 right here and then times n, which is going to be negative n and then 2 to the n like this. Very nice. Alright, now I will have to come back here because we still don't have the constant yet. Remember earlier, I had to bring out the differential equation again. When we had e to the 2t and then e to the t, what we have to do is you multiply this by a constant, multiply by that constant. You have to find out the general solution first, right? Well, I will tell you the following. Right here, our an, this right here has to be the form of, right here we have the homogeneous solution, which is 2 to the n. This right here is the one that you are going to multiply by a constant. So let me just put down our favorite constant, which is c. And this right here is a particular solution already. So I'm just going to minus n and then 2 to the n like that. So this right here is our general solution for this recurrence relation. But how can we find out what c is? Of course, as always, use the initial condition. A0 is equal to 5. So A0 equals 5. That will tell us, well, c times 2 to the 0th power minus 0 times 2 to the 0th power. On the left-hand side, we just have 5. This is just c minus 0, so c is equal to 5. So, final answer, an is equal to, this right here is just 5 times 2 to the n minus n times 2 to the n. Yes, this is the same as what we got earlier, because we can write this as 5 minus n times 2 to the nth power for our final answer, like that, right? Very cool, huh? Now, the third way is perhaps another way to explain why we have to multiply by the n right here. Without knowing that, I will just tell you guys the following, right? Do you guys remember your calculus 2, your differential equation? The part that you hate the most is that you have to use power series to solve differential equations. Yeah, I don't like that neither. That's the third way right here. Third way might be the longest, but hopefully comes more natural, I will say. Just let me know how you guys feel after all this, right? This right here will be using infinite series, and the particular name for this is called the generating function, right? So here we go. I will have to tell you guys what a generating function. I will just write this down for you guys. I will start with let g of x, and again, this right here is what we call the GF, namely the generating function. And again, this right here, it's not so crazy. It's just like a fancy name, right? I will say, because the generating function will write it as g of x for an, which is the one that we have. Let this right here, actually, I will write it down like this. This right here, again, it's just an infinite series. So you just go ahead and do the series. But you have to go from 0 to infinity. And then you just focus on whatever the an is. And then you multiply by x to the nth power. Again, whenever you have a sequence an, you can have a generating function by simply putting the an down right here. That's all. And then you can call this to be g of x. That's all. Seriously, that's it. And the difference between a generating function and your usual infinite series is that right here, we don't really care about its convergence. All we care about is the coefficient, because we're trying to find a formula for the an. So this is nicer in that sense. You don't have to worry about the if it converges or not. Yeah, just do the math. That's pretty much it. So let g of x be equal to this, and of course we're talking about that, and this is how we are going to do it. Have a look. We have the an right here, but this is only good if n is greater than or equal to 1. The generating function always starts with 0 to infinity. Keep that in mind. However, in order for us to use this, we can only sum this up from 1 to infinity, right? And I'm going to erase all this, and I'm just going to work out this right here for you guys. So here's the deal. I'm going to look at this, and I'm going to sum it up from 1 to infinity. So have a look. Here is the sum as n goes from 1 to infinity, and I'm just going to have the an here. And again, I will have to multiply by x to the nth power. That's the generating function? Almost. Because this is at 1. This right here is 0. We have to fix the index. You'll see. Anyway, because we're going from 1 to infinity, we can use this. So I can just put this down right here for the an. Namely, we get the series as n goes from 1 to infinity, parentheses this guy, which is 2an minus 1. And then we have the, 2an minus 1 minus 2 to the n. I'm so sorry. This is just not, I don't have enough space. I'm so sorry. All right, let me write this down again. Sum it up from 1 to infinity, an, and then multiply by x to the nth power. This is the sum as n goes from 1 to infinity. This right here, I will just replace that. 2an minus 1 minus 2 to the n. Then, this is not eta, this is n, right? Then times x to the nth power. This is not h, this is n, right? All right, anyway, just go ahead, just change that. Now, what we can do next is that we are going to fix this, and this is how. So keep this in mind. This is the third way, just keep that in mind. Well, I will have to come here because I have to work this out. The way that we are going to do this is that we are going to fix the power right here. I want to have x to the n minus 1. I will just take out one of the x because eventually I want to fix the index here. So fix the power first. So I will have x times the series. N goes from 1 to infinity. This still stays the same. And then the rest right here still stays the same. So we have 2an minus 1 minus 2 to the n times x. But this right here is n minus 1 power now, right? Then what we are going to do next is that right here, I'm going to add 1 to all the index right here. In the meantime, all I have to do to keep this balance is just minus 1 here, minus 1 there. That's the idea. So as you can see, this is x, and then this is going to be n going from something to something. But again, let's do this in order. I will have 2a, add 1 here, so it becomes just n, and then minus 2, add 1 here is n plus 1, times, this is x to the nth power now, right? And again, here we have to minus 1, which is 0, and infinity minus 1 is still infinity. Now, you can see that I can just multiply things out and all that stuff. And right here, I will have x times the first part, which is the sum as n goes from 0 to infinity. And I have 2 right here, right? So perhaps I will also put down the 2 in the front. And then here we have the an, and then x to the nth power. What's this? Yes, this is precisely our GF, namely generating function. Good. Now, minus, well, be really careful with this. You see here we have 2 to the n plus 1. Well, of course, this means 2 to the n times 2, and we can just put the 2 in the front as well. So I'll put down the 2 right here first. And then we have this x, and then we have the series as n goes from 0 to infinity. Then for the inside, we will just have 2 to the nth power times x to the nth power like this. Very good. And you'll see why I want to do this in a sec. But anyway, this is what we have. And then on the, let's just write this down right here real quick. This is 2x. And again, this is our generating function, which I will just write it down as g of x, right? This is from that. Then right here, we have minus. This right here is still our 2x. But what's this? Of course, you can write it as 2x in a parentheses raised to the nth power. And that should remind you of our best friend. Let me remind you guys right here. When we have our best friend, namely 1 over 1 minus x. This right here is nicely equal to the series as n goes from 0 to infinity of something to the nth power, right? All you have to do is put the x right here. That's all. Now, we just have to go backwards. So, the 2x will be the input. We just have to put it here. And then we have another 2x here. So all in all, we have to just have the 2x on the top. Let me just write that down right here for you guys. And then over, I'll just put this down in not purple, blue. over 1 minus, again, 2x, like that. Very nice, right? So now this is all good, but we should also be fixing this as well. Have a look. This right here goes from 1 to infinity. I really want to go from 0 to infinity. This is okay. Let me just go ahead and do this. I will just rewrite it as n goes from 0 to infinity of an times x to n's power. That's okay. But I cannot borrow one number, and that number is precisely our a0, right? I just add a0 here. But of course, if you add the a0, just go ahead and minus the a0, so we can keep that to be balanced. And we do know what a0 is. This is the same as that. And you know this is our generating function. So this right here is g of x. And then we can just go ahead and minus, well, the minus should be in black, minus. And the a0 is 5. And now have a look. The left-hand side is just g of x minus 5. And then, of course, on the right-hand side, we had this, namely 2x g of x, and then minus 2x over 1 minus 2x. I just had to bring this to the other side. And the reason I want to do that is because I want to solve for what g of x is. So now let's go ahead and do that. Bring this to the other side and factor out g of x. Let me just write it as 1, and that becomes minus 2x, and then we have the g of x right here. And then I'll have the 5 right here, minus 2x over 1 minus 2x, like that, right? Then, of course, we can combine the fractions. So you will see that I will actually solve for g of x right here for you guys. Combine the fractions, I need to have 1 minus 2x as its denominator. And then, of course, this times that, which is going to be 5 minus 10x, and then minus another 2x. On the top, I have 5 minus 12x. And then divide this to the other side. It's the same thing, huh? This right here is 1 minus 2x. Things are going to get a little bit weird. You will see. All right, keep this in mind. G of x is equal to this, right? And I'm going to erase this part. And the goal is that this right here, we have a rational function. If we can write this as a power series, we can just mix and match the coefficient. That's the approach, right? So here's the deal. Oh, man, I am going to break this down. It's not so bad. Have a look. G of x, this right here is equal to, on the top we have 5 minus 12x over, of course the bottom is the same as saying 1 minus 2x and then square. You can try to do this by partial fraction, or you can also just do the following. Have a look. On the bottom here, we have 1 minus 2x, right? Yeah, 1 minus 2x. On the top, wouldn't it be nice if we have 5 minus 10x? Because we can factor out the 5, and then we can cancel out the 1 minus 2x part. So, for the top right here, I'm going to write that as 5 minus 10x, and then of course after that, minus 2x. And then you see I will just go ahead and divide this by 1 minus 2x squared, likewise 1 minus 2x squared, like that. Factor out the 5, divide out the 1 minus 2x, then you see the first part is 5 over 1 minus 2x. That's it. For the second part, we have minus 2x over 1 minus 2x, and we have to face this. This right here, not so bad. Again, we are trying to go back to the infinite series form. So yeah. Anyway, this right here, use the best friend. We have the 5, yeah? So put that on the outside. And then n goes from 0 to infinity. Here is the input. I will just put down the 2x here and then to the nth power. That's it. Best friend always is the best. Trust me on that. Now for this though, we will have to utilize other friends. You still have to use your best friend. Namely, its derivative. So you'll see. Because on the bottom you have this square. Again, the 2x, just forget about that for now. Have a look here. We know that 1 over 1 minus x. This right here is the sum as n goes from 0 to infinity, x to the nth power. And if you differentiate this, on the left-hand side, work out your derivative. Trust me, you get 1 over 1 minus x, and then square. The right-hand side, you put the n to the front and then minus 1. And here's the deal. You get n x to the n minus 1. But if you have n start with 0, well, the first term will be 0, so it's not needed. You can just start with n is equal to 1 and then to infinity. So this is equal to that. And I did not forget about my chain rule. It actually is positive. I can go ahead and check out the differentiation. But again, we like to have n start with 0, so we do the same trick as what we did earlier. This right here, I will add 1, So I can subtract 1, and you see we will get n will be going from 0 to infinity, and then n plus 1, and then x to the nth power. That's what we want. Now, have a look. This right here is our input, right? So, here's the deal. Right here, I have the minus 2x. Okay, I don't have enough space. All right, let me just write this down right here. I have the 5, and then sum as n goes from 0 to infinity, parentheses, 2x to the nth power. Okay, minus 2x times 1 over this, which I will just plug in the 2x, right? Here is the input, plugging 2x in here. So I get the sum, which I should put this down in blue just to make it stand out for you guys. Here is the sum, or the series, whichever way you want to call it. N goes from 0 to infinity, and then n plus 1. And here we have the 2x. So be really careful. We still have the 2x here. Then you raise that to the nth power like that, right? So that's what we have. Now we have the 2x, and this is also 2x to the nth power. So of course we can fix the power here. So just focus on this right here. You see, just focus on this. We get the sum as n goes from 0 to infinity, n plus 1, and then this is 2x to the n plus 1 power, because I bring this inside, and that's what we have. There's a problem though. I cannot combine the infinite series. Well, don't worry. Fix the index, fix the n again. So let me just write this down for you guys. 5, and then the sum n goes from 0 to infinity. Perhaps I'll just write it as 2 to the n, x to the n, and then this is minus, of course, right? Now, this is what we'll do right here. I'm going to minus 1, minus 1. So in that case, I just have to add 1 here. So focus on this. You get the sum, or the series. N goes from 1 to infinity. And again, this becomes n. And this becomes 2x to the nth power like this. So this right here is the form that we have. But again, the problem is that this and that, they are not exactly combinable at the moment, but I can make it happen for you guys as long as we just do it carefully. Anyway, this right here is equal to 5 times the sum. N goes from 0 to infinity, 2 to the n times x to the n, right? Now, right here, I will have to minus, right? This was a minus, so let me just put on the minus here. And then here we have the sum. N goes from 1 to infinity. But if you have n goes from 1, okay, that's good. If you want to combine, you need to have n is going from 0. Can I legitimately change this to n start with 0 and then to infinity, and now copy down the rest? N times perhaps already as 2 to the n times x to the n. Is this the same as that? Yes. Why? Because when you have n is equal to 0, you put it here, that's just 0. It does not matter. So this right here, you can just change that to 0, and now you see the summations are both going from 0 to infinity, which is very, very nice. And better yet, both of them have x to the nth power. Oh my goodness. Oh my goodness. Now, finally, I'm just going to write this down right here for you guys. Here we have the sum. I will combine both of them together into just one. Well, inside here, we have 5 times 2 to the n, yeah? And then minus, this right here is n times 2 to the n. And then both of them have that x to the nth power. So of course, I will just factor it out like this. Remember, this right here is our g of x, which is supposed to be the sum as n goes from 0 to infinity of a n times x to the nth power, because again, that's our g of x, namely our generating function. This match, so of course the coefficients must match because we have an infinite series. As you can see, oh my goodness, this is so much fun. An is equal to 5, well, of course, that's factor out 2 to the n because we want to be the same for the other ones as well. 5 minus n times 2 to the nth power. Oh my god, that's it, man.